Okay, so once again, I'm going to use some of the Math Learning Center videos that I've made. So this is a video from the Math Learning Center. I hope you enjoy. In this problem, we're actually going to use the change of variables rule to do an integral. Now we want to integrate the function x plus y over the region that's the trapezoid given by these vertices. We're going to start by sketching this region and just forget that I've given you this transformation. And we're just going to ignore that transformation now, sketch the region, and then hopefully you'll see why integrating this over a different region is a little bit better. Sketching this region, we only need the right half plane, so I'll draw the whole y-axis and just the positive x-axis. And now I'm just going to sketch each one of the vertices. And now I'm just going to draw the line segments in between the vertices. The equation for the green line is y is equal to x, and the equation for the dark blue line on the bottom is y is equal to minus x. Now, the orange and the light blue lines, those equations might seem difficult, but just recognize that the orange line, for example, is the right translation and up translation of the dark blue line. So if I do a little bit of scratch work down here, unfortunately it goes off of the screen. We see that y is equal to minus x minus 5 halves, that's the right translation, and then plus 5 halves, that's the upward translation. And so this is equal to minus x plus 5. And similarly, the equation for the blue line is y is equal to x minus 5. Attempting to integrate over this region is not impossible, but it's kind of aggravating because no matter whether we choose the y integral on the inside or the x integral on the inside, we're going to have to split this up into two integrals. So that's what happens if we did the y integral on the inside, but we have something similar if we did the x integral on the inside. We'd have to split it into the bottom and lower halves. This is what the given change of variables does. It will transform this region into a more convenient region to integrate over. So we have the u and the v-axis drawn. Unfortunately, the computations I do below do not come through because I did it out of the recording area, but you can just follow along at home on your own. So the green line becomes 2u minus 3v is equal to 2u plus 3v because y is equal to 2u minus 3v and x is equal to 2u plus 3v. So rearranging, this gives v is equal to 0. Now the orange line, the left-hand side is y is equal to 2u minus 3v. So for the orange line, that equation becomes 2u minus 3v is equal to minus 2u plus 3v plus 5. And rearranging this, we see that u is equal to 5 over 4. Using similar methods as this, we see that the blue line is transformed to v is equal to 5/3, and the dark blue line is transformed to u is equal to 0. And so I will sketch all of those now. And so now I can begin to do the integral. I'll do the v integral on the inside. This goes from 0 to 5/3. U goes from 0 to 5/4. Now we're integrating the function x plus y, but x is equal to 2u plus 3v, and y is equal to 2u minus 3v. And so we can simplify this and we get the integral with the same u limits as the one above, and of course the same v limits as the one above, and the function that we're integrating is just going to be 4u dv du. For the v integral, u is a constant, so this is just 4 times 5/3, the integral u equals 0 to 5 over 4 u du. The antiderivative of u is 1/2 u squared, so this is now 4 times 5/3 times 1/2 times 5/4 squared. In other words, 15 or 25 over 16. And this is equal to 125 divided by 24. So this is the region that we began with on the left, and the region that we integrated on over the right. On the right-hand side, the region on the left is R. The region on the right is T inverse of r. The region on the left is not so difficult to integrate over, but the region on the right is much easier to integrate over.